Okay, so let's continue where we left off last class. So quick summary of last class's of yesterday's class. Okay, so this we have done this before, but primarily series parallel connections you already know, right? A parallel connection is one in which the two terminals of the both the terminals of the two elements, two or more elements are connected together at two nodes, right? That's a parallel connection. A series connection is one where you take two elements and connect only one node, right? Not both. And there is nothing else. The intermediate node is not connected to something else. Otherwise, it's not a simple series connection. And you can apply for this series or parallel connection, okay, for the complex or the aggregate voltage and current quantities, okay, can be defined in terms of the individual voltages and currents, and you can arrive at relationships for between these as well as the equivalent element that could be connected between those two nodes. Okay, we took the simplest cases of resistors, okay, in series and parallel. You can arrive at the equivalent resistance, okay, of an element that would replace this more complex combination of two or more, okay, a single element, okay. And it's, for example, if the two or more resistors are in series, the equivalent resistance will just be the sum of the resistances. When the resistors are connected in parallel, the conductances will be additive, okay, that is shown here. Similarly, for inductors, it's very similar to resistors. You have them in series, they are additive. If you have them in parallel, the inverse of the inductances are additive. In the case of the capacitance, it's exactly the opposite. If they are placed in parallel, the capacitances are additive. Okay, when they are placed in series, the equivalent capacitance is inversely additive. Then we looked at more complex, different kinds of elements apart from the passive elements. If you take active elements, of course you can place two voltage sources in series, no problem. You cannot place two voltage sources in parallel unless the two voltages are equal. Okay, if those two voltages are equal, the equivalent source is just the same source. Any one of these sources would act as the equivalent source because the voltage is the same. It's an ideal source. Similarly, two current sources can be placed in parallel but not in series. Okay, so this is the analog of the voltage. Okay, if you place them in parallel, the overall current is I1 plus I2. You cannot place two ideal current sources in series unless the two currents are equal. Okay, and as I pointed out, voltage sources cannot be shorted. It's a corollary of the previous result. Current sources cannot be left open. Okay, ideal voltage sources cannot be shorted. Ideal current sources cannot be left open. Okay, and there are other cases, right, which you can think of, putting two or more elements together, and you can figure out whether it can be done or not. The last thing we did in yesterday's class was putting a voltage source across a capacitor, perfectly fine. Putting a current source across a capacitor is also fine as long as you realize that there is no steady state, right? What you have been thinking of a steady state may not be possible, but you can actually find out what the voltage across the capacitor will be as a function of time. It is quite easy. Okay, it's a very simple circuit. Any questions on yesterday's class before we move on? Okay, fine. So coming back to the subject material, couple of more definitions before we move on to a very important topic. So far we've been assuming that in an electrical circuit, different elements are actually connected using wires. So in this course we will assume that wires are ideal. Okay, they are ideal connections between terminals. Okay, so in other words, so let us say I have two resistors, R1, R2. Okay, this is one possible connection. Okay, this is another possible connection. They are both the same. Both are ideal wires. The second one is just a bad drawing, I guess you could say. Okay, but as long as they are connected by wires, there is no element there. We will assume it's an ideal wire. What is an ideal wire? An ideal wire has zero resistance. Okay. In other words, it's also called a short circuit. Okay, that I mess up. It's also called a short circuit. I hope all of you have heard this term short circuit. How many of you have not heard the term short circuit? Good. Okay. So how do you define a short circuit? How do you define a short circuit? Between, of course, a short circuit is defined between two nodes, okay, 2 points. So how do you define it? Both are at the same potential, exactly. So in other words, a short circuit means okay, the voltage difference is defined to be 0. If you say there is a short circuit between two nodes, the voltage difference between those two nodes is 0. Okay. Similarly, going back, you do not say anything about the current as far as the short circuit goes. Okay, it may be defined by something else outside this. Similarly, I know I said a wire is ideal and you know there is zero resistance and so on. It is also assumed that a wire can carry any amount of current. Okay, it can carry, it's an ideal wire, it can carry any amount of current. Okay, can carry any current. So a short circuit is defined as a voltage difference. So if I take two nodes, of course a short circuit means there is just a wire between those two nodes, right? There is zero resistance. You can represent it in many ways. The minute I say zero resistance, R equal to 0. So let these two nodes be A and B. Now of course, the minute it's a short circuit, you don't need to represent it by two different node names, right? Because nodes we assume are unique, so we will not name them. Okay, so R equal to 0. Any other possibility to represent a short circuit? You can put an ideal wire, you can put a resistor and say the resistance is 0. Can you do anything else? You can put an inductance and say the inductance is 0. Very good. And L equal to 0 between two nodes makes it a short circuit. Okay. What else? There is one more possibility. Huh? Capacitance equal to infinity. Okay. Capacitance equal to infinity does not exactly capture everything about this. So we will leave that for now. We will come back to that. A fully charged capacitor. No. Remember, the definition of a short circuit is that the voltage difference between the nodes has to be 0. Okay. So you can say it's an infinite capacitor with no charge across it. Okay. But what is that the same as? A 0 volt voltage source. Okay. Okay. And this you will use in many places. Okay. Since somebody brought it up, we'll just look at that. If I have a voltage source of value V0, okay, that is the same as an infinite capacitance charged to this voltage V0. Okay, you will also use, these are all very useful properties, knowing things like this. Okay, an infinite capacitance charged to a voltage V0 will be indistinguishable from a voltage source of value V0. Why do I say this? What is the property of a voltage source? It maintains a constant voltage difference between those two nodes while supplying any current. Let us assume you have this infinite capacitor. What is the total charge on the capacitance? It's infinite. So even if there is any current flowing from the capacitor between the nodes of the capacitor, the voltage across it will not change. Right? What you are saying is the capacitance is infinite, it cannot get discharged. Okay, so it will continue to maintain a voltage V0, okay, while supplying any current. Okay? The other kind of connection is an open circuit. Okay. What is an open circuit? I have two nodes A and B. Okay. And there is no connection between them. Okay. Or infinite between them. So in other words, this is the same as R equal to infinity between the two. What else? It's a zero current source. Very good. And finally, you should realize that it's the same as a capacitance of value 0. Okay. Basically, fundamentally, this infinite resistance comes from the point, this is actually a derived quantity. What you are saying is current is 0. Right? The current between those two nodes is 0. Is that clear? This is the original definition. Just like where we said the voltage difference between two short-circuited nodes is 0. The current flowing between two open-circuited nodes is 0. Any questions? Very good. So now suppose so let's say this was V1, R1. I give you some circuit like this and say I want the voltage across this resistor. How would you do it? I'm sure you have seen very simple circuits like these previously. How will you do it? Huh? Can you raise your hand? See, the problem is, as far as I can see, there's a sea of students, okay, with 150 students. I'm not even able to make out who's answering, okay, even people nearby, especially with the earpiece in my ear. So please raise your hand. I think somebody, was that you? Okay, you. Okay, yeah. Okay, so find the equivalent resistance. So now that you know what series and parallel connections are, you know that this is, the resistance looking in here is R3 plus R4, right? You can find out this will be R2 parallel R3 plus R4, okay? You can find out the resistance here is R1 plus R2 parallel R3 plus R4, right? Then what will you find? What will you find? You can find out the current flowing out of the voltage source into this complex equivalent resistance, okay? Then you apply the conditions for current flowing through series and parallel connections. In other words, you are implicitly using KCL and KVL in some form. You just reduced it to a very simple form, right? Okay. So this you probably know how to solve because it's a very simple circuit. But now we need to find ways to analyze more complex circuits, okay, and find out a systematic way to do this, okay, not just ad hoc, right? As it turns out, there are multiple ways to simplify the circuit. This is what you know. There are other ways to simplify the circuit also, okay, which we will learn later on in the course. But first of all, we need to find a systematic way of doing this, okay. So first, what we want to do is we want to do it for any network possible, right? That is what we want to do. This is a very specific network. If I had given you a different circuit, okay, you would have approached it differently, right? Okay, so I have some network N, okay, and in fact we'll even take an example of a network, okay. Let us take only this example, why not? We'll take the same one, R1, R3, R4, V1, right? So how do you find out? So this has some we have seen this before. How many elements does this have? Five elements. Okay, how many nodes does it have? 1, 2, 3 and 4. Correct? Okay. How many loops does it have? Okay. Now based on these, can you figure out how to write KCL, KVL and so on? Are you sure? Okay, so let us try to figure this out. You have 4 nodes, right? How many KCL equations can you write? 4 KCL equations. How many independent KCL equations do you have? Why? Why are there only 3 independent? Somebody, yeah, you said 3, right? Why? If I gave you a very complex circuit with some n nodes, right? Of course you can write KCL at each one of these nodes. It will always be valid. But for a general network with n nodes, how many independent KCL equations can you have and why? What? Somebody said some number? N minus 1. Why is that? Potential difference. KCL has to do with currents, right? It has nothing to do with potential differences yet. At some point? Okay. It may not be happening at one point, right? It may be, see, currents get added up at every node and they get added up to 0 because there is no charge accumulation, right? That is what we have been saying. But for any general network, how can you say that there will only be n minus 1 independent current KCL equations? Yes? Sorry, can you please raise your hand? Can't see. Yes. All the current will originate at that point. No, because you might have, KCL is written, when you talk about voltages, you talk about potential differences. Okay, so when you talk about KVL, I can understand, okay, maybe you take one node as a reference node. Right, here we are talking about KCL. So there is no talk of reference nodes yet. So as it turns out, we'll take a very general example to try to understand how this works, right? So we can try to represent the circuit, okay, in terms of what is called a graph. Okay, any circuit, any electrical circuit can be represented by what is called a graph. What is a graph? So it's a representation of the electrical network, okay, with lines representing each element. You no longer have the element. What you retain are only the nodes and the connections. Okay, so what we'll say is of the network retaining node and connection information. So in other words, if I actually take this previous circuit and try to draw a graph of this particular circuit, of this particular network, what will that look like? So I have 1, 2, 3, 4. I have 4 nodes. Okay. So I'm going to take 1, 2, 3, 4. Now I need to draw a graph representing the circuit. What do I have? I have V1 between 1 and 4. Very good. So I'll make that connection like this. Okay, I have R1 between 1 and 2. I'll make that like this. Okay, I have a circuit here, I have a connection here, and I have a connection here. Is that clear? Just note that very often, for convenience sake, circuits are drawn with a rectangular figure, but this is actually just a wire. This whole thing is just a wire. It's the same node. Okay, so just remember that. So you will represent the whole thing by just a single node. Correct? Is this a representation of this particular electrical network? Okay, very good. Now, each one of these is called a branch. Okay, any interconnection between two nodes is called a branch. So a branch is basically something which stands in for the element in the graph. Okay, by the way, these are not very formal ways of defining what a graph is and what a tree is. This is for you to understand more easily. Okay, so this is called a branch. Okay, so topologically you have all the information that you need from the graph itself. You don't have any element information. Okay, now what we are trying to set up the graph to try to understand how to solve these or analyze the electrical network for a more complex system. That is all, right? So, but what do we mean when we say we want to analyze the electrical network or know the electrical network? We saw this yesterday. What is it? For every element, you need to know the voltage across it and the current through it. Okay? Once you know that, you have everything you need to know about the electrical network. So our final, our final goal is to find out all voltages and currents. Is that clear? So suppose I take a general network. Okay, I have B branches. Okay, N nodes. Okay, B branches and N nodes. What is the total number of elements? It's B, right? Each branch stands in for an element. The total number of elements is B. Okay, the total number of nodes is N. Okay, so remember that the total number of nodes, you can take the same set of B elements and create multiple networks with different number of nodes. Okay, it depends on how you connect them. So you can have some N nodes which is independent, okay, which is not directly related to B. Is that clear? Okay. What do I want to know? I want to know the voltage and current information for every element. Those are the variables that you want to solve for, that you want to analyze the network for. How many variables do you have now? You have 2B variables, correct? So we want to solve for these 2B variables in some fashion, correct? Okay. So we are going to try to use the information from the graph to try to get as much to decide how to get information about the KCL and KVL equations, because what the graph holds is the connection information, right? So it holds the node information. Okay, it can also, so you can, it also holds the potential difference information. You can define the voltage of each one of these nodes. Just because this is not a wire, this is just a branch. Remember that this is not a wire in the graph. It doesn't mean the potential difference is 0. Okay, so this graph has the voltage and current information that you need. You need to extract that out. How are you going to solve for these 2B variables? You're going to solve for it using certain sets of relationships. So KVL, KCL, and there is a third bit of information that you need to use. How many equations does KCL give you? okay, we are going to see that it's n minus 1. N equations can be written, okay, but only n minus 1 independent equations, and let us see why that is. For each one of these I can write, let us say we'll assume the references all, sum of all currents leaving the node is 0. I can write the same thing here. I can write the same thing here. Now the interesting thing to note is that KCL was based on very general arguments, right, of charge conservation and what else? And no local accumulation of charge. So I can actually create any random surface or agglomeration of nodes and also write KCL for that. Okay, KCL, we happen to define it very early on in terms of interconnections between elements, but it can actually be written for agglomerations of nodes also. It can be written for surfaces and so on. So in fact, if I decide to exclude all the, if I decide to exclude just one node and write agglomerate all the other nodes in the network, whatever, however complex it may be, okay, the sum of the currents leaving that agglomeration should also be 0. And you can very clearly see, if you exclude, if you take a surface which includes all other nodes except for one, okay, there is a relationship between the current leaving the nth node and what you write for the surface, and there is also a relationship between what you write for the surface and all the KCL equations you write inside. Okay, I hope this is intuitively clear to all of you, right? Because of this, you will always get only n minus 1 independent KCL equations. So in other words, KCL will give you n minus 1 equations. What about KVL? How many equations can you get from KVL? And how do you figure that out? We want to know independent equations. Okay? Okay? I take the same B elements. Okay? First of all, let's take this simple circuit. How many KVL equations can you write? You can write 3 equations. You can write as many KVL equations as there are number of loops. How many independent KCL equations can you write? That is what we want to find out. In this case it's 2. Why is that? Because the minute you write it, so let us number the loops. So I have one loop here, I have a second loop here, okay, I also have a third loop here. Okay, since you are only talking about potential differences, okay, for this simple circuit it's very clear, right, that the equations which you write for loop 1 and loop 2 will also be related to the one which you write for loop 3. Okay, there is some commonality between them. If I have given you a different network, okay, the number of dependent and independent loops will keep changing. Okay, so for a very general case, how do you figure it out? So as it turns out, you can, based on the graph method, it is a little bit easy to figure out what this is. So we will take the example of this graph itself, okay, for this simple case. So we are going to define a tree, okay, of the graph. So note that the graph itself is a representation of the network. So you have every element inside it. The tree is a sub-network of the graph, okay, with two very important properties. One of them, okay, is that it needs to contain all nodes of the original graph. Okay. The second property is that it should contain no loops. Okay. For any graph, okay, you can build a tree, okay, that contains all nodes, okay, without forming any loops. We can take the simplest case and try to form trees from this. So this was the original graph. Can somebody give me an example of a tree? I'll give it to you. This is one example of a tree. Okay. As somebody pointed out, a tree. This is one example of a tree. Okay. You can draw many trees. Okay. All you have to do is draw one tree. Okay. And proceed further. So we can take which one? Shall we take this one? We'll take the third one, the T one which we have drawn. Now what we are going to do, we are going to take this tree and start adding branches such that they complete loops. Start adding branches, okay, such that they complete loops representing what was a connection through an element in the original graph. You can't draw it arbitrarily. So in other words, I can't draw a link like this because this was not contained in the original electrical network. What are the two options? I can draw one here, I can draw one here. Correct? The number of ways in which you can do this, are you able to see the color? I added this left arm, I added this arm and this arm. Okay? So these two are the two ways to complete the graph, okay, or create loops, okay, by adding in one extra branch to the tree. Okay? The number of ways in which you can do this, tells you the number of independent KVL equations. This can also be shown. This is beyond the scope of this particular class, but you can show this, okay, using graph theoretical methods. So you can take the example of the other graph, okay, the other tree, okay, and I can complete it in this way and I can complete it in this way. Okay, you will find that any tree you choose, you keep adding branches to create loops, okay, that will give you the number of independent KVL equations. Is that clear? Any questions? Okay. So of course I have a more complex network. So let us say 1, 2, 3 and so on. I have n. Okay, this is an example of a more this thing. You can choose any kind of tree that you want. Okay, so you can choose a tree like this and so on. Okay, it doesn't matter which tree you choose. You are only using the information to find out the number of independent loops. So for a general case with B branches and n nodes, okay, how many can you draw? Any ideas? Huh? B minus n plus 1. Why is that? Who's that? Is that you? Okay, why is it B minus n plus 1? So to start off, we have B branches and so it's B minus n plus 1. Why is that? Through KVL, KCL. Yeah, but you can do it for a general case, right? How do you do it from KVL, KCL?
No, I assume the n equation from KCL.
Okay.
And totally that should be the variable.
Okay, that is not the way to do it. We should do it the other way. We are trying to do it the other way. So of course the answer is right. It is B minus n plus 1. The question is why it is B minus n plus 1, right? Okay, I want you to think about this and tell me next class. Okay, I want you people to think about why it is b minus n plus 1, but this can be shown. Okay, you can get b minus n plus 1 independent KVL equations. Okay, so he's of course approached it the reverse way, because as you'll see, we are trying to lead towards why a network can be solved, not the other way around, right? So next class I want somebody to tell me, at least one person hopefully will come up with it's a very straightforward answer. Okay, so you can create b minus n plus 1 independent KVL equations. So let us go back to this. Independent equations. Okay, so how many equations do you have now? B equations, but you have 2B variables. You need a third bit of information. What is that? What is there in each branch? What is there in each branch? There is an element. So what information do you get from the element? The voltage to current relationship of each element. Okay, of each element will give you a further, it will give you a further B equations. Is that clear? Together how many equations do you have? You have 2B equations, 2B independent equations. You have 2B variables to solve. It can be solved, right? Once you solve that, you will have everything you need to know about the network. Is that clear? Okay. So let us say I take this network. I1 and I2, and I have, so now I'll start off by naming the nodes. How many nodes do I have in this circuit? How many nodes do I have in this circuit? Okay, N1, N2, N3, N4 and N5. Remember again, this is an agglomerated, right? It's just, I've just for ease of drawing, I've drawn it. It is just the same node. So I have 5 nodes, right? Okay. Now how do I start off writing this? How do I start off analyzing this? So I'll even name these R12, R23, R34, okay, R25, R35 and R45. I'm just naming them based on the nodes between which they are connected. Okay. Now I can start writing, there are many ways to start approaching this analysis. We will start by writing KCL. You can start writing KVL, you can start writing KCL. Okay, we will start by writing the KCL equations. Okay, so this is called nodal analysis. So we can write KCL equations. How many independent KCL equations can you write? How many independent KCL equations can you write? 4, right? So 4 equations, independent equations. So you will have to choose 4 nodes out of these 5. Which nodes will you choose and why? Huh? You can actually choose any one of them. Of course, it will give you the answer. So I guess from the point of view of having least number of terms, if you write an equation at 5, it will have actually lots of, okay, variables, right? You can see N5 is the node to which lot of elements are connected. Okay, so that the term for that will actually have the equation for that will have many terms. Okay, so we will start off writing the equations for the other nodes, okay, because it will be easier, that's all. So we'll make this the reference node in some form, because we are not going to write KCL here. Okay, remember that voltages are always potential differences, right? It's not the voltage of any node is only represented with respect to some other node. So when you write the KCL equations, okay, to go further, you'll also need to write out the voltage variables. Okay, so we will write the voltage of this as V1, this as V2, this as V3, and this of V4 with respect to the reference node. Okay, the voltages which I have named here, V1, V2, V3, V4, are with respect to N5, which we call the reference node. Okay, because when you say you know all the voltages and currents, what you mean is with respect to something, right? Voltages, if you know, you can always say with respect to this node, the other node is at this voltage. That is what you are saying. Okay, so KCL, you can write down 4 equations. So what is the equation for N1? Can somebody tell me what is the equation for N1? What we are going to do, we will follow this convention in the class. Sum of all currents leaving the node is 0. You can also follow the other convention, it does not matter. In this class we will follow this convention. So sum of all currents leaving the node is 0. Okay, so what does it say? What is the current leaving N1? So you have minus I1, right, plus V1 minus V2 by R12 is 0. Correct? Okay. At N2, V2 minus V1 by R12. Okay, that is the current leaving this node in this direction. Okay, plus V2 by R25 plus V2 minus is 0. Okay, this is the KCL equation at node 2. At N3, okay, this current plus this current plus this current is 0. R35 plus, sorry, V3 minus V4 by R34. At N4, okay, you have V4 minus V3 by R34 plus V4 by R45, okay, minus I2. Okay, these are the 4 KCL equations that you can write. These are the 4 KCL equations that you can write. You can already see I have actually incorporated multiple things. I have already incorporated the element relationships inside. Okay, I have already incorporated the fact that through the resistor V equals IR. Okay, that is why I was able to write these in very simple form. Okay. Now we are going to rearrange these things in a very specific way. Okay. The way we are going to do this is, how do you solve a set of linear equations if you have many of them? What is the easiest way to solve this? Determinant. Oh, yeah, using the matrix form, right? You set up the equations in a matrix form and then solve it, right? So let us say we are able to set it up in some form. We want to set it up in matrix form. Okay, so we are going to use a very specific matrix form. We are going to set it up such that you have a matrix times a vector equals another vector. Okay, so we are going to set up our equations in that form. This, the vector on the right hand side of the equation, is going to be the vector of all independent current sources. Okay, so this vector is going to contain it is going to contain independent current sources plus some, maybe some zeros. That's what I mean. Okay, this is going to be the vector of the voltage variables that we want to figure out. Okay, and this, what do you think that will be? Think about it. We have written or drawn up the equation for this simple example, right? What will that contain? Conductances or resistances, okay, in some form. Okay, this will be a matrix consisting of resistances and conductances, but it will have a certain, as we will soon see, it will have a certain pattern. Okay, it will have a certain pattern, and we want to figure out what that pattern is. What will that pattern depend on? In what form will it be? Look at the equations. So you are going to have to rewrite these equations such that, for example, this I1 you are going to push to the right hand side of the equation. Okay, this one is going to be 0, this one is going to be 0. Here I2 is going to move to the right hand side, right? So you are going to rearrange it such that the independent currents, in this case I1 and I2, are going to be on the right hand side. So you can already tell what your right hand side is going to look like. What is it going to look like? I1 0 0 I2. That is what the right hand side is going to look like. So as I said, it is going to consist of independent current sources. Obviously there may be nodes in the network where there are no independent current sources connected to that node. There you will have 0. Okay. V1, V2, V3, V4. Okay, that is your vector representing the independent voltage variables, right? And here you have the matrix corresponding to the conductances or inverse of the resistances. Again, you can rewrite these 4 equations by combining all the terms which are the coefficients of V1, V2, V3, V4 for each one of these equations and fill in that matrix. So I want you to do that tomorrow. Okay, do it as a homework, come back with this matrix filled in and we'll try to figure out where the pattern is. Okay, so we'll stop here for today's class.